Hello and welcome to QED Stata 5 from part S13. I'm going to get this data from the worksheet Madagascar. So this is what it looks like. Slightly more variables this time, but only 22 observations. And these are the 22 different regions of Madagascar. And all this data is real data that I've assembled from different sources that are easily available. So let's just import this data and then we're going to create some variables to show per capita malaria cases. So we find the do file for this. And I've saved the Tajikistan data and going on to this. So here's load it in, creating per capita variables. So generate a new variable is equal to malaria in 2010 divided by population and 2014 divided by population. It's somewhat of an approximation because I only have population figures for the latest census, 2018. So I'm dividing by that population. Obviously, it would have changed, so it's not precise, but at least it's controlling for the size of the population, so it's improving it. So we should do that. Data's come in, and that's what it looks like. These are the names of the 22 regions. There's no need to code these, they only occur once, and it's fine for that to be string data because they're just names. Everything else is already in numeric form, so that's fine. Very easy to understand. And here's the two new variables in malaria cases per capita in the 2 different years, so they're pretty small numbers, as you'd expect. Okay, so using a suitable size test, assess whether the sample provides evidence that it rose between 2010 and 2014. Okay, so what we're doing here is we're trying to compare the malaria levels per capita between 10 and 14. So has this risen to here? So what we could do is compare the mean of this with the mean of this. However, it's much better to use the fact that we know that this is the same province in each case. So the same region, this is the same region, the same region, the same region. So they're matched up. So we can use a paired test, which essentially is finding the difference between each pair here. So remember that's built into the paired samples test we've done before, and it's built in as a single command. So we can just enter that into the do file as like this. The paired test. It's just testing whether this is equal to this by essentially doing a t-test of the differences. So excuse that. Didn't excuse it. I think I pressed something. Right. That's better. So it's tearing the test, and what we're trying to find is it's risen. So the null hypothesis would be that the mean level in 2014 is the null hypothesis would be that the mean rise between 2010 and 2014 is 0. The alternative hypothesis would be that the mean rise between 2010 and 2014 is positive, is greater than 0. So it's a one-sided alternative. We're looking for the greater than 0 alternative. Well, it's written the other way around, so it's looking for this one here, but it's because it's subtracted the other way around. So that's the change from 2014 going back to 2010. It's negative. So it's a very small number. It's a very small number. So not surprisingly, it's not significant. So if there has been no change, then the chance of finding a sample as large as ours, 22 different provinces, would be 0.17, 17%. So no, there's no real evidence there that we can reject the null hypothesis, and no real evidence that there's been a change in malaria or an increase in malaria. So there's no evidence there to just support that. Right, we can quickly look at the correlation between all those different variables, because there are many different arguments you can make about why various things can be related there. So for example, poverty is correlated, or we might imagine poverty would be correlated with the state of not having had any education up to even primary level. We've done that before. This time, if we put the sig on it, that'll give us the result of the correlation significance test, or the test of correlation, to tell you whether or not you could get a correlation that strong randomly. So what we'll do is we'll do that and then picture it as well by drawing a correlation graph for it. So let's give us the graph. So you can see the graph there looks as though there's a positive correlation, and it's quite clear positive correlation. And when we look at the correlation coefficient, 0.417, yes, it's a positive correlation coefficient. And here, this time we've got this p-value here. So this is a p-value of the null hypothesis that in the whole population, the correlation coefficient between, and if you did, in similar circumstances, if you observe this thousands of times, those 22 provinces, keeping everything else constant, then you'd get a correlation as, if there was no real connection between those two factors, you'd get a correlation as strong as this 2 times out of 100, so it's less than 5%. So this is less than 5%, so you can reject the null hypothesis that there is no correlation between poverty and having no education. So it seems that this is a significant correlation that corresponds to something out there in the real world. So that's just an example with poverty and connected with one factor. It would take a long while to go through all the possibilities like that. So what you can do is very quickly, let's do the whole thing. Let's finish this part of the analysis. You can very quickly, instead of just putting 2 variables in, put a whole list of variables, and it finds out all the possible correlations between them in a matrix. Not only that, but as well as doing that, it puts stars on the ones that it says to put stars on here, and it also gives you in visual form as a whole lot of scatter graphs. And taken together, that's a very powerful way of exploring possible correlations between lots of different factors. So maybe we'll start with the graph. So these are the factors. So for example, here, primary and secondary education, obviously clearly positive correlation. You can look at all the correlates of poverty. So poverty and phones. So more poverty, people have fewer phones, more phones, there's less poverty. Though I'm not saying that's a causal correlation, but why would that be? In areas where, in regions where people have more phones, there's less poverty. In other things correlated with poverty, that's the one we just looked at. More poverty, less education. No clear correlation with primary education, but it seems that more poverty, lower secondary education and lower tertiary education you'd expect. Malaria, slight increase in malaria cases with more poverty, and no real clear correlation with population density in any of these things as far as you can see with the eye. So population density doesn't seem to be highly correlated. It's slightly surprising perhaps. Malaria correlated weakly with a few things. Let's turn to the correlation coefficients, because some things are better to judge by eye, because there can be some correlations that the correlation coefficient doesn't pick up because it's a non-linear correlation, some sort of curve or shape like this, which the correlation coefficient might not get, because this is assuming a linear correlation. But you can see that connection between poverty and phones, very big number, big negative correlation, and also very significant. So the chances of that happening, the chances of picking out a selection of 22 measurements and getting a correlation as big as that randomly is like, it's never going to happen, 1 in 1,000. So that, be confident that there's something going on there. Confident there's something going on here. There's a 2.6 in 100. This one, we have negative correlation between poverty and primary education, 0.24. That could happen 24% of the time. Something as strong as that just randomly. So that one we can discount. This one happens very rarely, so that's a big negative number again. More secondary education, less poverty. More tertiary education, less poverty, very strongly correlated. Malaria, more poverty again. That's quite a low chance that of getting that if there's no connection. So probably there is a connection there. Population density. Yeah, the only one that population density is related to is no education yet. So in areas of higher population density, you're much less likely to find people with no education. So it says most people that migrate to towns probably then are people who have got at least primary education. So you can pick out all the ones with a low the low p numbers, the ones where you can reject a null hypothesis that this is just a random thing. So low p numbers means there's something in there. This is reflecting something going on outside the sample in the real world. So a lot of connections of tertiary education and secondary education with different things in the direction you expect. So it's always the direction you expect. So there's no results that are going opposite to what you think. More secondary education, more people with phones, marginally significant there. And some of these are put stars. The stars are because it told it to put stars on. That's what this means here. So it's anything that's significant of 5%. So anywhere where the sig level is less than 0.05, put a star because that draws the eye to it. So you can see the ones with the stars are the ones where we can be reasonably confident, at least at 95% confidence level, that there's something going on beyond the sample to explain this correlation. It's not just purely a random effect, like some of them could be, like this one, for example. Okay, so I think that's enough. Sorry to go on. I hope you've given up watching if you're getting too bored of me talking about that. But there's so many correlations thrown up by just one command in stata. The bar chart, the charts, and the correlations. You can spend a lifetime exploring the possible reasons for these connections. Okay, now on to the next example, which is to Cambodia and healthcare. But for now, thanks for watching.